Now the topic is some side effects issue in parallel computation. So when we do parallel computation, we have to be careful to investigate whether there is some possibility of side effects. I'll try to explain with an example. Say to add a sum of a parallel list. So we have a parallel list and we are trying to calculate the summation of all the items in that parallel list. Now, to do that, a simple strategy can be declare a var type variable and then use a for each clause to get each item in that list, and we can increment the value of this var type sum with the current item, and we traverse all the items and finally we hope to get the total sum. But unfortunately that will not be a safe strategy, and soon we'll see that we can get erroneous results out of that because there is a possibility of side effect. Here the same example with some more details, and here we are declaring that sum as var type initialized with 0. Then this is a parallel list and we are using for each to get each item in the list, and we increment the sum with that current item, and finally we check the total sum. So we hope this will give us the correct result, but that we can test is not the case. So let me run it quickly on my system, and this should be the code which I have copied from there, and let's run this code. And this time Scala reports the sum as 4000 something. Let's run it again. Oh, what happened? This time the sum is 3000 something. So same code, if we run multiple times, we are getting different results for the sum. So obviously things are not happening correctly, correct? So let's investigate. Maybe we can think about it, that why this is not happening correctly. Because this operation that incrementing this sum variable is happening parallelly for these 100 items. So think about the situation. Say we are talking about item 1 and item 2 among these 100 items here, and say this line we are trying to increment sum with item 1 and item 2, and those two things are happening parallelly. Now if those two things happen at the same time, what does it mean? That means the increment effect of sum for both those things will not be reflected, right? One right operation will nullify the another right operation, as an example, and that can be the source of error. I hope that makes sense. Now what are the fixes to address this issue? One fix is we can just use a lock in this way. So this dot synchronized locks this operation where the sum is incremented. So in that case only one item can be added to sum at one time, and other operations will wait for this. Other items being added will wait for this. That fixes the problem. The other fix maybe looks very simple, is just to use this reduce function available in Scala. So this is the parallel collection. We can say that collection dot reduce. Reduce typically means an aggregation function, and we are doing the aggregation with plus underscore. Remember, this is a shortcut of writing this anonymous plus operation. We can have also an extended form, but doesn't matter now. So reduce operation, reduce is an aggregation function which takes this anonymous sum operation and applies to all items, and reduce takes care of the locking by itself. So this is the fix 2. I will not go into detail, just to understand that not all operations are associative operations. Subtraction is not an associative operation, and for non-associative operation, using a par collection doesn't make any sense, and there the reduce will give us non-meaningful results. So that doesn't make any sense if you think about that. But for non-commutative operation like string concatenation, it makes sense. So given a bunch of strings, we can use reduce with concatenation operation to concatenate all of them using reduce. That is fine. One example, list here is a parallel collection, and we are using for each and x is mapped to x plus 1, then that is printed. The question is, what will be the output? Will that be a sequential, like 3 maps to 4, 4 maps to 5, so on, or will it be random? And as we saw before, when we are using parallel collection, things happen in random order. So B should be the answer. Now let's talk more about map reduce style. We already got some idea. Let's see more. Say a list has 1 million items here, and let's talk about some arbitrary operation. Say we want to add plus 100 to each item. So we want to use a map map with this anonymous function. So map will apply that anonymous function to each of them, which is displayed here, and that will be the first result, right? The result of the map, this part. So and this is displayed here, and that operation is, that means these operations with these 1 million items, this map operation, this part, are happening can happen parallelly if we use dot par here. So you see that list2 dot par we are using, so this operation can happen parallelly. And after we get this output from this parallel operation, that can save a lot of time compared to the serial one, then it's time to apply reduce to get the total sum of all these items. And remember that reduce operation, as this is an aggregation operation, using parallel doesn't make any benefit, anyway the lock has to be used, right, as we discussed before, and only one item can be added to the total final result at one time, and reduce takes care of that locking by itself. So remember, only the map part is parallelizable but not the reduce part, but this total things together is called map reduce style. And in practical problem, typically what happens, this part, this map part is more expensive. There are more work, more work to be done, and when those extensive work happen in parallel fashion, that saves a lot of time. And then even if reduce is not happening parallelly, that's fine, still we have already saved a lot of time. Okay, so this is one example. We are using dot par of this list, then map using this anonymous function multiplied with 2, right? So that means what? That means this 1 will be multiplied with 2, producing 2. 2 will give us 4, 3 will give us 6. So we got 2, 4, 6. and then reduce plus will add them together. So even if things are happening randomly in this part, that means when parallel operation happens randomly, reduce will put them together, so ultimately output will be 12. Doesn't matter whether this part is random or not. Now let's come back to our example of using web pages and try to get the total size a bunch of web pages. So here we have bbc.com, cnn.com, and say we want to get the total size of these two pages. It's a small example, there can be 100 pages, and we'll come to that. So we already saw how to do it sequentially, right, in our previous example. Now this time we want to see how to do this computation parallelly. So this is the function get page size concurrently. What happens here, this parallel version of this collection we use, and then we map each URL to this functionality, right? So that means for each URL we get the size and then print something and return the size. That is how this part is working. And that means that when we say sizes equal to this function, that returns this length from each item, each URL, right, as an list, correct? So that means this sizes basically is a list of these two pages lengths. We have to see that, correct? Because the return of this map for each URL is length. So from these two URLs, two lengths will be returned as a list, and that will be the sizes. Right, so sizes is a list of length of BBC and length of CNN. And then when we say sizes dot reduce plus, that will apply the reduce operation on that two items in the list, and we'll get the total size. And as we all just discussed, that this map operation is happening parallelly, not the reduce operation, and that is okay, because the operation which is inside the map, that is the most expensive operation. That means to download a web page, that is the most expensive operation in this example, and to download these two web pages parallelly are saving a lot of time. Is it yeah, so this is the pictorial view of doing similar thing on n number of URLs. So this is the list of URLs which we want to download, and then we want to get the total size of all URL as final result. So what is the different phases? In the first phase we use map and apply this function get page size on each URL, correct? So that will give us a list of sizes here, and this operation can happen in parallel. That is the most expensive operation, and that means happening it parallelly saves a lot of time. And then reduce can do the aggregation and get the final result. Maybe it's a good idea to run this piece of code, because in my opinion it is super interesting to see how parallel computation can save time in real life. This is really a real life example, like crawling different web pages and downloading them and doing something with that, right? Just like web crawler. So let me go to my system and let me copy things, and here's BBC, CNN.com are there, right? We will download and then we'll run concurrently. So let's run them, and things have happened and there is no problem, correct? So things have happened concurrently. Okay. Now, some developer who is not aware of the side effect issue, which we discussed before, can follow this erroneous path of doing aggregation. In this example, say we want to compute the number of all images in all links. So we have bunch of web pages, bunch of URLs, and each URL basically means one web page, right? And inside that web page we can have zero or multiple number of images, correct? So each URL basically gives us how many images are embedded in that URL page. And for some reason we want to compute the total number of all images in all these links. Say that is the goal. Now some developer erroneously can declare some as var 0 and then a parallel collection of these URLs. I'm going to this map. So for each URL, get the URL as a string, get how many image is there in that page, and dot length means how many, right? And that is the number, and we try to increment sum with that number, and that will be erroneous because there is no locking. The right way of doing the same thing will be get the parallel collection and then use the map similar as before, and here get the page, get how many images are there like before, right? Remember that image regex is the regular expression of the image, how an image link looks inside an HTML page. We talked about that before. And then here, given a page, we are searching how many matches are there, and dot length gives us that number, how many matches, right? So num basically means how many images are there in the page of the URL, and then that happens for each URL, right? And so counts basically is a list of all those numbers over all URLs, and then we use a reduce operation to aggregate them. That was basically a MapReduce style. Similarly before, we can also do use MapReduce style for math computation. Some math computation can be expensive, right? So if we can use MapReduce in a proper way, the parallel computation can save a lot of time. Typically this sort of computation is a good candidate for parallel computation. Before we go to parallel, let's see how serially we can do the same thing. So get a list of 100 numbers because the sum is over 1 to 100. Then map each I, basically x is I here, to this function, right? X cube plus 2, that is the first map. And then we have to again do to the power of 4. So use another list and apply map on the previous list with this anonymous function, which corresponds to this part, that x given the input, we are going to power of x, power to the power of 4. So that is done, and then for this summation we use the reduce on list 2. That is the serial way of doing it. Now to save time, we can do it parallelly. First get the parallel collection and then just do the same thing, and that can save a lot of time. So pictorially what we are doing with this n number, first we use this operation 1 in our picture. First example, this was the operation 1, and let's call this one is operation 2 and this one is operation 3. So how the picture glows, operation 2 means another map on this previous result, right? And these map phases can happen parallelly, as we just discussed before, because this result does not depend on this result, they're independent. This result also does not depend on this result. So you can see that these map operations can happen happily in parallel fashion, and that takes the most amount of time, and we are saving a lot of time using this parallel computation, and then the reduce and get the final result. Just another style, we can concatenate the previous different lines in just one line using dot. Self-intuitive. And here are some help how to handle exception when you are trying to process a web page. Okay, thank you.